Hello. The purpose of this video is to examine some basic principles of how to design an experiment. We're going to look at this from a pretty broad perspective. We're going to also introduce some vocabulary here and hopefully give you a chance to start to wrap your head around it. We're also going to look at a couple of specific examples. So why don't we start by looking at some of the basic principles of experiment design from the lens of saying, why would you want to do an experiment as opposed to, say, an observational study? Keep in mind that in an experiment, we actually impose a treatment on our experimental units or subjects. And then we measure some variable of interest, and we draw a comparison from a group who received the treatment and a group who received either a different treatment or no treatment. And what we're looking for is significant amounts of difference in between those two groups to show that our treatment had some sort of effect, measurably, in one way or the other. Keep in mind the effect does not have to be a good one or a positive one, just simply an effect. And if we can do that, we can actually say, if we follow all the different procedures here, we can say with some assurance that our treatment was actually the cause and that the effect was measured as we saw it. Otherwise, if we do an observational study, we can make a note of differences between groups, but we can't draw any cause and effect relationships. So experiments are really powerful and definitely something we want to use anytime we have the chance. Let's look at three big principles of experiment design that we're going to be using here. And the first one is that we always want our experiments to involve what we call replication. Replication. Now, replication is often misunderstood because we think about it from a perspective where we say, oh, somebody else should be able to replicate or duplicate my experiment by following my procedures. That's a principle from science, and it's completely valid. It's just not what we're after here. In replication, what we're really looking at is we're looking at subject-to-subject variability. Okay? And we're saying from one subject to another subject, we can have some variability. Maybe subject number 1 is tall, and subject number 2 is short. And if they were our only subjects and we gave a treatment to subject number 1 and did not give it to subject number 2, there may be a difference between them that's actually just because subject 1 is tall and subject 2 is short. And there's not really any effect of our treatment. So what that does, you can imagine, you could say, well, gee, we could have some tall people and some short people in each group. But basically, that gets really tricky. If we're using the principle of replication, what we're saying is, what if we had, instead of having subject 1 and subject 2, what if we had, say, 50 subjects of various heights in one group, and then we had something like 50 subjects of various heights in a second group? We would say that there's some tall people, some short people, some in the middle, and so anyway, any variability we might see that's due to height between the two groups would be sort of accounted for and sort of washed out by the large number of subjects that we're including. So basically, we want to use enough subjects to reduce chance variation. Use enough subjects to reduce chance variation. That's the notion of replication. How about the next one? Randomization. This one's a little bit more obvious in its meaning, and it says this. You spent all kinds of time earlier learning about samples and different types of samples and how important it is to choose random samples. Well, this is saying that each subject needs to be randomly assigned to treatment. So assign subjects, and of course we could say units here, assign units or subjects to treatment randomly. And if we don't do this, we're going to be in some trouble. It becomes very important that we don't make any guessing, we don't use any judgment. We simply say we're going to let random chance choose if you're in the treatment group, in the control group, or whatever other group you might happen to be in. And so that's the notion of randomization. It's extremely important. We can't ignore it. The third big principle of experiment design has to do with control. And you may have heard the term control group, and they're related, although they're not exactly the same thing. Okay? We want to try to control as much as we can. This notion of control is the idea of saying, let's try to identify any variables that we're not currently planning to measure that could affect the outcome of our experiment, and then let's try to account for those in some way. So for example, if you were doing an experiment on obesity, and you had a group of subjects that you were going to assign to treatments to say if a weight loss program works or not, well, it would be pretty difficult if one entire group had people who had way more weight to lose than the other group. So you had basically all your most obese people in one group and all your less obese people in another group. That could possibly skew the results because maybe people who have a smaller amount of weight to lose would respond differently than people who have a lot of weight to lose. And you could say, gee, these people lost a lot of weight, but maybe they had a lot more weight to lose in the first place. So when we deal with control, we try to identify lurking variables before we conduct the experiment, and we try to account for, we try to mitigate those as much as we can. Usually, we do this in part just by having a control group. This is a form of control. And so what we're doing with our control group is we're saying I have to have something to compare it to. If you put a bunch of people through a weight loss program, they might lose weight. But they might lose weight just on their own without your program in the first place. So the most basic form of control is saying let's have a group of people who don't get any treatment at all. And they're going to be a good comparison against our treatment group. So we have control, replication, and randomization. And just to review, we want to control the effects of lurking variables on our response just simply by comparing at least 2 or more treatments. And usually one of them is no treatment at all. In replication, we're looking to try to reduce chance variation by using a lot of different units or subjects. And in randomization, we're trying to use chance to assign our units to treatments so we don't have any problems there. We're going to look at an example of how we could design an experiment and how we could create a diagram that could show our experimental design. And this is going to be a very simple one. And again, this is one about weight gain. So let's imagine for a minute that a food company is assessing the nutritional quality of a new instant breakfast product by feeding it to newly weaned male white rats. We're talking about rats here, so we're just going to call them units. The response variable is a rat's weight gain over a 28-day period, so basically over a month. A control group of rats eats just a standard diet. There's our group that we're not doing anything to. Otherwise, they're treated exactly the same as the experimental group. Now, we're also going to introduce a little bit of vocabulary here. This experiment has one factor. That's the diet. And the diet has 2 levels. They either get the new instant breakfast or just the standard. The researchers are using 30 rats for the experiment, so they have to divide them into 2 groups of 15. Here's how they do this in an unbiased fashion. They put the cage numbers of the rats in a hat, 1 to 30. They mix them up, and they draw 15. Those rats form the experimental group. The remaining 15 make the control group. So each rat has had an equal chance of being selected to be in the SRS. Okay? Here's the design of what the experiment could look like. Once we've done the random assignment of drawing the rat numbers out of a hat, that's the first thing. That's pretty much always going to be the first thing on your diagram. That creates group number 1, and it creates group number 2. Group number 1 has 15 rats, and group number 2 has 15 rats. So in our diagram here, we're trying to say what groups we have. Sometimes we could have 3 groups or more groups, and how many subjects or units are in each group. Now we're going to identify the treatments. So we're going to say first, group 1 is going to undergo treatment number 1, and that's going to be the new diet. That's the new group. And then group number 2 is treatment number 2. And they are eating the standard diet or the old diet. They are the untreated group, the control group. All right. So now what are we going to do? We need to sort of bring our diagram back together by saying, what are we going to measure? So for these two groups, they're going to come back together after the 28 days are over, and we're going to compare something. What are we comparing? Well, their weight gain. So what we would be measuring is the difference by subtraction between their final weight and their initial weight. And so we could then use those numbers to do our data analysis, which we're going to learn how to do later on. But this is what we call an experiment design diagram, and it's one that you can certainly use. We're going to see this format used often in our study of experiment design. Let's take a look at a slightly more complex one. This time, in this example, it's about utility companies. And let's say that a lot of them have programs to encourage their customers to conserve energy. Let's say that we wanted to have the electric company put meters in households to show what the cost would be if the electricity use at that moment continued for a month. If a consumer could see that, would they reduce their use of electricity? And those are kind of expensive, so would a cheaper method work almost as well? So they decide to design an experiment to find out. A cheaper approach is just to give customers a chart and information about how to monitor their own electricity use by using their own meter. And the experiment's going to compare the meter that's placed there, the sort of electronic one, versus the chart, and also with a control group who they don't get any help at all. Because some of them may reduce their usage just because, well, of whatever reason. What we're trying to measure at the end is the total electricity that's used in, say, a year. So let's say that the company starts with 60 single-family residences that are all fairly similar, so they're kind of interchangeable. And they want to use 20 in each of their groups because now we have 3 treatments instead of 2. So after they undergo some sort of random assignment, we're not really as concerned about how they assign them in this problem as to what they do next. This time we're going to have 3 groups. We're going to have group 1, and I need to write a little smaller. I'm going to run out of room. That's going to be 20 houses. Group 2, also 20 houses. And group 3, which is 20 houses again. Again, we have 3 groups because we actually have 2 treatments plus we have a control. So group number 1 is treatment number 1, and they get the meter in their home, which actually gives them a display and a readout and does some of the math for them. Group number 2, or treatment 2, group 2 gets treatment 2, which is they get the chart and they get some information about how to chart their electricity use, and group 3 gets treatment 3, which is nothing. They're the control. Okay, so we identify who's in the group, how many, and what treatment each one receives, and then what are we comparing at the end? Well, remember that we're going to compare their use of electricity. And that is going to be done for all 3 groups. We're going to measure the same thing for all 3 groups to see if one group has significantly less electricity use than the others. So I hope these examples are useful and give you some idea about how you can design an experiment.